Okay, so good morning, everyone. So we will continue our study of non-inertial frames, and so let us recall. We had this setup where we had one set of coordinates and frame rather, and yet another one O prime with its own and there's a separation which this was this R vector. Okay, so this was the setup, and so we assumed that the basis, which is the right-handed triad, these had dependencies. Right? And then we also defined D okay, and so this was a property of the frame. And we identified it with angular velocity. Okay, so are there any questions about this part of the setup? Okay. So then we said, okay, so let us, so we considered the simple case where R was 0, that means the origins agree, but we can always put this back as I mentioned. Okay. And so we saw that then an arbitrary position vector or displacement vector would be this is in the O basis, O frame, and this will be equal to, of course there is summation which I am not indicating, which you know. Okay, so given this we started to evaluate. We saw that there was a velocity which we could associate to this, it's dr by dt, and we were doing it in the second frame, and so we got the following thing. We saw that it was so while in the other frame it would so books write formulae which confuse me for sure. Okay, so they write something like d by dt in O, I guess, is equal to d by dt in O plus omega cross. Okay, so I mean, I just want to warn you about this danger. Okay, so yeah. You're going to ask me to explain this? I won't, because I'm not wasting my time understanding that.
So there should be a O prime.
What should be there?
D by dt in O prime.
Okay. Thank you. Okay. So so let's get back to this. But we had started the computation for the second derivative, which was t square r by dt square. Okay, and I did complete the calculation. It was just one more line, so hopefully you people have done it too. Okay, so this is what we get, and I have to tell you what alpha is. It's a rate of change of omega. Okay, so it's angular acceleration of the frame. Okay, so the point here is that usually we would have called acceleration. So in physics, we identify a vector with its components. Nothing wrong with it, but it comes with some price. So in the O prime frame, we would just say x1, x2, x3 primes is the components of x. Okay, which is correct. But further, what happens is that similarly, we will say acceleration. Acceleration will be identified with, and jumping, I could even write for velocity, x1 double dot prime, x2 double dot prime, and x3 double dot prime. Okay, so coming back to this, if you look at this, this is truly the acceleration, full proper computation, and we see that that's only one of the terms. Okay, so if you wanted to make Newton's law, F, if there is some external force acting F equal to ma, you would have written m d square r by dt square. But what is happening is that this is equal, so in components you will write something like this. So Fi equal to, m xi double dot, plus there is a whole bunch of stuff, plus other terms. Okay, so this is component of force in O prime basis. Okay, so EI prime I should write. Okay, so but from this formula we see that there are three other terms, 1, 2, and 3. Okay, so plus three other terms. So what people try to do is to take, so you rewrite this as saying m xi double dot equal to fi minus three other terms, the same terms with a minus sign. Okay, so now they have pushed it to the right hand side, and so these are called pseudo forces. Okay, and they all come from the fact that we are in a frame which is non-inertial. Frames are time dependent. I mean, that's it. Okay, and you can see that all the three terms vanish if your frame was not time dependent, and then it agrees with this thing. So this is the origin of the term pseudo forces. Okay, so again, I mean, nothing wrong with doing this, but somehow I feel that the picture, this way of thinking about it is less confusing. And so we'll just name all these various terms, so that I'll call them terms here because they are not forces unless you choose them to the other side. So this term has a name. Does anybody know what it's called?
Centrifugal force.
Exactly. Not force, centrifugal term. Okay, and this is, yeah, and this is the angular acceleration term. I won't give it a name, this one. But this one is an interesting one. It only acts on, it's non-zero only when you have, xi dot being non-zero. That means in the O velocity, in the O prime frame, there is some non-zero velocity. You need that, okay, for this to work. And this is an interesting thing, and it's called the Coriolis term. Okay, so minus of all these terms, so minus of centrifugal term will be called centrifugal acceleration. You have to multiply by m, right, to make it force. Similarly, Coriolis term will become minus of the Coriolis term will be Coriolis acceleration. Okay. But in this course, we will not move it to the other side, etc. Again, this is standard textbook material, and it's my. I feel that it confuses a lot of things. Okay, so is this clear? What is going on? Okay, so we get 4 terms. Okay, 3 beyond what we would have expect. 3 more than what we expect. Okay. Any comments? Okay. So now what we will do is we will illustrate. I will illustrate. So with a nice example. Okay. So those of us who live on Earth, right? We live on Earth. We live on the surface of Earth. Okay. Which is a non-inertial frame. Why? Why is Earth a non-inertial frame?
because there is a pseudo force.
Earth is rotating.
Earth is rotating. Okay. There is also motion around the sun and then in the galaxy. But okay. But the dominant one is the fact that we are rotating. Okay. Why? I mean, Earth is rotating. And what is the period?
24 hours.
24 hours. Okay. 1 day. Okay. So that is the thing. So let us now set up the problem. So let me just. Okay. So let me draw some things. Hopefully I don't struggle. Let's draw surface of Earth in this different color. Ah, lucky. Okay, so what we are going to do is the following. We will choose O to be at the center of the Earth, which is our axis, and we will choose the rotation axis as E3 cap direction. Okay, and it rotates with some frequency omega. Okay, so omega is omega E3 cap. Okay, this is what I'm going to do. Okay, so and I will also to 0th order. I'll say that this axis of rotation is the same as a North Pole. I don't know which axis is North Pole, whatever. There could be, there is various axes. So we just take this as our model, okay? And then suppose we are at some point on Earth here. We'll take the origin to be that point. So it's O prime. Okay, so I'm not indicating E1 and E2. It will be some, some stuff like this, right? So E1, E2. So I'm going to delete this because I want to draw some things. I will also delete O prime and put it later because I want to add some more structure to this. Why is it doing this? It's supposed to draw a straight line. Okay, so I got something to work. Well, let me move my X. It's simpler to make the X move. Okay. So this is the R, okay, and so this angle will be theta. So we are at some point on Earth, which is here, okay. So what is the relationship between latitude and theta? Let L be latitude.
So theta is the latitude, right?
No, because equator is 0.
R cos theta.
No, latitude is pi by 2 minus theta.
Oh.
If we say north, right? When, North Pole is 90 north and South Pole is 90 south, right? So if we say south is negative, right? This will work, right? So L equal to 0 is North Pole. Sorry, theta equal to pi by 2 is L equal to 0. Okay. Does this make sense? So this is latitude. Okay. So now I will, so this is our O prime. Now I can write it. And I will choose, my first thing I will do is choose the vertical direction. So think about this as Chennai. And so we are here. And so this is, we'll call this Z axis, Z prime axis. So we'll call this E3 prime, which is in spherical polar coordinate systems. It's ER of theta and phi. Okay, is this clear? And then we will choose E2, or rather E1 prime, to be E hat of theta. And finally, I need to choose what E2 prime is. E2 prime is, if you wish, E3 cross E1. Okay. So it comes out of this plane, but I'll just write it out in. Okay, is this clear? So we have defined. So now I have defined for you a basis for O prime. Is this clear? Any questions? Okay. So now I'm going to take, let's say, R be any point, and let's say that X, Y, and Z are coordinates. I won't put prime, okay, because we are not interested. Coordinates in the O prime frame. Okay. So R will be X E1 prime plus Y E2 prime plus R plus Z E3 prime. Okay, notice that R is also so. Okay, so this is a case where R is non-zero, capital R. Okay, that's what we have. Is this clear? Everybody is okay with what I have written here? I have shrunk it so you can see the whole diagram. Okay. And now question 2 is what is omega? Is of course omega E3 prime, but what I want to ask you is what is it in the prime basis? Anybody?
So one thing I'm not getting, why is the Z component, I mean E3 hat component R plus Z?
Because I'm doing it with respect to the frame O. So it's like this, right? So
Oh, okay.
in that too. Yeah, I chose this. This R is non-zero in my example. I just did this calculation, but okay, I'm just putting that in.
Yes, sir.
Okay.
Got it. I thought we were doing it on the surface.
Yeah, we are on the surface, but I'm writing this R, which is like a universal vector, right? I mean, it doesn't matter. I'm writing it in the basis of O prime. That's all.
Okay, sir.
In the basis of O prime, why would R, capital R come?
Oh, so what the observer O will say? Okay, let me just paraphrase what I'm saying. Is that so the thing is, I want to measure everything. This guy with respect to I have to take into account that with respect to this fixed frame O frame, there is a shift of origin. So the origins don't coincide. That's all.
So on the surface, wouldn't the R plus Z, the Z be zero on the surface?
No, but no. You're on the surface and you're picking some point X, Y, Z in your frame. That's all.
Oh.
So you will just say X, Y, and Z. You know, O prime fellow, as somebody is correctly pointing out, will just say X, Y, Z. What is the vector? It's X, Y, Z. But what I'm saying is that it's related to the O guy in this fashion. So now my question is, what is omega? Okay. So, I mean, I thought you guys noted.
Cos theta E3 dash cap
Hmm.
minus sin theta E1 dash cap.
Thank you. Okay. So this completes the various definitions that I wanted. Okay. So let me expand it back to normal size. Okay. So this is what we have. And so what I want to do is to compute first the centrifugal term. Yeah, this is horrible. Let's set it for simple. I want to compute this. Okay, and what is the centrifugal term? It is just omega cross omega cross R. Okay, wrong color. Okay, so if we do this computation, what we get, I am going to skip some steps. Okay, so we get one term. Okay, this is what you will get. Okay, so this is the guy coming from this term alone, R E3 prime, and there is also plus uh, omega cross x e1 prime plus y e2 prime plus z e3 prime. Okay, so yeah, one more way to understand why we need the R is also because the axis of rotation of the rotating frame is really passing through O. I mean, if you want, that's another reason to think about that. But here now what I've done is I've separated the centrifugal term into two terms. Okay, one is really a property of we would have written since we are in frame O prime, we will write everything in terms of what we have, x, y, and z. But now what we see here is that there is a first term which does not depend on anything. It's just a feature of where we are on Earth. It only depends on latitude. Okay. And what is this one's effect? Okay. Suppose I did the following thing now. Okay. I took a simple bob, plumbing bob or with a heavy mass. Okay. And so first thing is, let's look at this. In what direction is the gravitational force?
-E3
Acceleration?
dash.
Minus E3
Minus,
hat.
right? It is g times minus E3. Right. Okay. So that's what, so I need to, and I'm drawing this in the E1 prime, E3 prime plane. Okay. So what you will find is because of this term, and let's assume that x, y, and z are so small that we can neglect all these things. Okay, so we just have to, we want to ask what is this first term doing, and that's what I want to explain. So let's draw the vertical here. And I'll just call this theta tilt. Okay, theta t for tilt. So if you have a bob and it's not moving, okay, I claim that it will not make, you will find that it makes an angle with E3. So this direction is E3, that this is a stationary plumb line. So this is what we will call vertical, because, right, this is, any plumber will come, right, they'll come with this heavy thing with a string and they'll hold it, right, so that they will know that's a vertical. But what I'm saying is that the vertical guy will make some angle with E3 prime. That's not the radial direction. Okay? And so what we will get is that there is a G effective. Okay, so what I'm going to say is that this term can be absorbed into a G effective, and that will look like this. Let me first do one computation to show you this.
Sir, but it won't happen in the North Pole, right?
Yeah, but I'm interested. I mean, if this term vanishes in some particular point for some value of theta, I'm okay with that. Yeah, because you put theta equal to 0, that term vanishes. But we are asking. I mean, you're in Chennai. You're not at. You're much more closer to, theta equal to pi by 2, or it's not pi by 2 also. Okay, so what I'm saying is, yeah. So this guy. So the thing is that so the tension, yeah, the tension. Okay, so it'll act like this. There's a tension, and it'll be balancing a G effective. Okay, so what we have to do is look at this. So we'll get T cos theta tilt will be G minus omega square R sin square theta. Okay, and T sin theta T will be the other, T sin theta T will be along E1 prime, so that will be omega square R sin theta cos theta, is it? Yeah. Okay, So the tan of theta tilde will be the ratio of these two guys, and that will be omega square r okay, now I'll do this. I'll write one step and then I always try to jump, not necessarily a good thing. Okay, and so G effective. So what is G effective? We can work out what G effective is also. So okay, is this point clear? And so we can also we can do a little bit more simplification. So is this clear what I've done? So all I'm saying is that because you cannot person who see if you're going to use a simple pendulum with small oscillations to measure G, you are not going to measure actual G. You'll be measuring G effective. Is this clear? Hello? Is this point clear? Okay. So that's what I'm going to do. And now we can, so I just want to massage this a little bit better. Tan theta t, you can write it as, there's a dimensionless quantity which comes. Okay, omega square r by g into sine theta cos theta divided by 1 minus same dimensionless quantity r by g into sine square theta. Okay. Now we can do, so you can see that this is just property of the planet, right? Of Earth in this case. So we can compute this exercise. Compute this for Earth. Okay, it's dimensionless, check that also. And claim is that it is around 10 power minus 3, which is much, much less than 1. Okay, so you can see that we can approximate. So this quantity in the denominator is much, much smaller than 1. Okay, so we can even write something, a formula for Earth is approximately okay, this is approximate for Earth. But decent one. Okay, and so and we can also do one more thing, that there is this term here. What is the dimension? What is so the displacement? So there is something which is omega square times displacement. Okay, that is the term. Okay, so now that that will be so. But the displacement in the O prime frame is typically much smaller than the radius of Earth. Okay, so it's small compared to G. Okay, so this term, it's also there, is order omega square is what I want to say. Okay, so this is the just to estimate what this term is doing. Okay, so what we have done is to get the dominant contribution, which will go off, and what remains is just the second line here. And I mean, it's there. It's not here. Where is the second line? Yeah, this second line. Okay, is this point clear? Okay, so now we have taken care of the centrifugal term. So let us now try to study Coriolis force. Okay, so in fact, one of my friends
Sir,
once, yeah, go ahead. Huh?
Coriolis term is said. We are
Thank
not
you.
taking it till that
Yes, yes,
time, sir.
absolutely. I'm so happy. Okay. So, I mean, see, for instance, there's no way we can, G effective is something which doesn't prove that the earth is rotating. But this term can be used to prove that the earth is rotating. Okay. So let us, okay, and so this, there is a nice object, there's a nice way of doing that, and it's called the Foucault pendulum. Let me get the spelling right. Yeah. Okay. So let's. Okay. Before that, let's do one thing simpler. So I'll do this later. I want just even simpler example. Okay. So let us so examples. Okay, the first one is suppose we have we go to some height h and drop a mass and it comes down to earth. Okay. So what? How much time does it take to? So s equal to half h equal to half gt square. Okay, and so and t will be 2h by g effective, g square rather. So t will be square root. Okay, so if we were not in some rotating frame, it would have fallen. And so, and what is this? And it hits the ground. It hits the ground with speed at, right? So it's just some for half mv square equal to mgh or whatever. So with speed square root of, I won't keep writing gf. I'll just write it as gh. Okay. So this is the standard thing which you know from high school. But now what happens now? But there is now we can see that xi prime dot, or rather in this case x3 prime dot, is not 0. Actually, it should even be, G effective also as a component along this thing. So let's ignore difference between G effective and G because it's a small effect. It's 1 part in 10 power minus 3. Okay. So let's do that. So let's solve this problem. Okay. So let's track. So let's solve for the equations in the non-inertial frame. Okay. So let us do the computation. We want to compute, and so we'll just say that. Let me do that. X3 dot prime is not 0. So that's all I need to compute. So I need to compute 2 x3 dot I. Wait, let's write the first right to get it done. Okay. So we can neglect, like I said, this is approximately only x3 we will take. Which we'll call as z dot. No? So this is, we can just write it as z dot. Okay, so if you just work this out, this is equal to 2 z dot. So omega had minus sine theta times E1 E1 cross E3 is minus E2. It's plus 2z dot sine theta. Okay, so what does it say? So what I am doing here is that this is falling in the z direction, and because of that, it's picking up a deflection in the E2 prime direction. Okay, along the E5. That's what you get. Okay, and so this is the y direction. So what we will get from here is that y. So this is just y double dot. Should be 2 z dot sine theta Ez prime t. Okay, and we will just we're going to do it recursively. So we'll just say that z dot is so this will be z dot will be equal to just minus gt. That's the standard. So I'll plug this in here. So we get y double dot equal to minus 2 gt omega. Oh, I forgot an omega somewhere. Yeah. Okay, so we'll get y of t will be t square by 2. See this thing, so that will be minus. Sorry, I'm not so good at. I have to do it. Where a and b are integration constants. Okay, so and at t equal to 0, say y of 0 is 0 and y dot of 0 is equal to 0. So when you let it down, we let it down with just we just drop it in the z direction, so there is no y displacement. So this just tells you that y of t. So a and b, this implies a and b are 0. So y of t is a cubic. So you should see a deflection. Okay, and then we can plug things in. But t, what is the time it takes to fall? Again, 2h by g. So what you will get is that the deflection that you get is minus omega g by 3 into 2 8g by 3 by 2 times sine theta. And so we can also, I'll rewrite this in terms of something dimensionless. So it will be this, you can show is minus h by 3. So I have to redefine some things. 8 omega square h by g. If you remember, omega square r by g was dimensionless. So this is also that way, by half times sine theta. Okay. So exercise, compute. By the way, you have to check carefully that I haven't made some sign mistake. I've been cavalier about what is force, what is term, etc., etc. So you need to, but actually you don't need to, because you need to check that. Okay, so exercise, check the sign, check my sign. Okay, where is the error? The error is here. Okay, I wrote something, right? I wrote y dot, y double dot, y double dot. Okay, check sign here, and let me know next lecture. Okay, so compute B for Earth. Okay, say H is, say, 10 meters or 100 meters. How much will this deflection be? Okay, so it will be very, very small for sure. Okay, so this is, but you can compute it, and this will be part of your problem set, I believe, because I haven't made it yet, but it will now come there. Okay, so is this clear what we have done? What I'm not particularly interested in the sign here. I mean, it is important, but more in the magnitude. Okay, so we already see that when omega square r by g was how much? 10 power minus 3. And what is the radius of Earth?
6.4 into 10
6,000
power
meters.
6,000?
6.
6,000 meters?
400.
6,400 kilometers.
Exactly, 6,400 or 6 into 10 power 6 meters. Okay, so this h here is, even if it is 100 meters, it's about 10 power minus 4. So it'll be quite small. Right, so, but there's a half, so it'll, 10 power minus 2 smaller than this thing. So you see that this will be a fairly small effect, but still worth asking how much this would be. Okay. So please do this. So now we will today, for the rest of, I'll take about 2 minutes to just set up the example 2, which we will continue. It's a Foucault pendulum. Okay. So the idea here is that you take a very long, and the length is usually of the order of, tens of meters usually. Okay. And then you start making it oscillate. That's pendulum. It's like a small pendulum. Okay, simple. Okay, and let's say we do it like this. E1, you start it out in, say, E1, E3 prime plane. Okay, you start doing this oscillation, but now because there is a velocity, we will see that there will be a deflection. This will get deflected. So this will, so the Coriolis term will push the bob out of. Okay, so if you look at it from top, what we will see is that if you look at it in E1 prime, E2 prime plane, if you look at the bob, it will no longer be, if it were just, if there was no Coriolis force, you would see it going like this, back and forth. Okay, this is without top view. Okay, with Coriolis, what you will see is that there will be some kind of oscillation. So it will no longer be planar. This is with Coriolis force. Okay. So next lecture we will solve this problem in full detail. Okay, we'll solve this problem in full detail and we'll work out what is the trajectory of this pendulum and what is its time period, blah blah. All these details we'll work out. Okay. And the thing here is that so it will be this will depend on latitude, obviously. Okay, so because it depends on latitude, you can use it to measure latitude. Okay, so you can use it to prove that we are in a non-inertial frame. B is to compute to measure latitude. Okay, so this is what we'll work out next class. So I think I'm done for today. I will pause for questions and comments. And
Sir,
yeah,
you said we cannot say the Earth is rotating with the help of centrifugal force.
yeah,
Why
because the
is
effect
that?
is very, very small.
Okay.
Because the part you absorb in G effective you cannot see, no?
But theoretically we can know.
No, we are not. Theoretically, you can measure it on every spot on Earth and plot with respect to, for G from this thing. But Earth is not round. We assumed it's a sphere. There are so many things which will mess you up. Okay, so what I'm saying is this is a way we will see This is a clean way of seeing it. Okay, even this falling mass, right, from some height, 100 meters also won't give you a big enough reflection. But okay, so this is a very, very observable thing. That's all I'm saying.
Okay, sir.
See, I mean, you could have this alternate picture where Earth is just, just this ball which is just stationary, and the universe is rotating, going around us, right? Then if Earth was just a stationary, non-rotating ball, then you wouldn't see anything, right? None of these effects should be there. So then it will be just regular gravitational effects. No centrifugal, no nothing, right? Okay. Any other questions?